We're live on YouTube. Yes.
Awesome.
Thank you, Alec.
All right. Professor Daley, are you ready to be introduced?
I am ready whenever you are, John. Can you hear me?
I can hear you. I'm as ready as I'm going to get. So it is 2 p.m. in Chicago, which means it's time to welcome all of you to our weekly VAMOS seminar. Our speaker this week is Professor Andrew Daley from the University of Strathclyde in Scotland. Andrew got his Bachelor of Science in Physics and Math from the University of Auckland, and then a Master's of Science also in Physics from Auckland, and then his PhD from the University of Innsbruck under the supervision of Peter Zoller. He, I have to say, is one of the broadest and most influential theorists in the cold atom quantum science community, having led works on all sorts of the most important developments in cold atom many-body physics, from things like developing TD-MRG techniques for modeling dynamics of atoms and lattices, to Rydberg physics, alkaline earth atoms, sub-wavelength addressing, quantum magnetism, and so on. He's really been sort of pushing the forefront of the ideas that we as experimentalists should be thinking about. One of my favorite results of his is this idea that one can measure entanglement in many-body systems through a generalization of Hong-Mandel interference. And not only is this sort of a wickedly clever idea, but it also points in a very deep way to what entanglement actually means. So with all of that said, I'm really looking forward to what Andrew has to say to us today about dissipative many-body physics with cold atoms. Before we move forward, though, I'd like to remind all of you to please ask questions. If you are in the Zoom webinar, you can do this through the Q&A. If you're on YouTube, you can type them in and we will gather these questions. There will be 2 question breaks during the talk, and then we'll have another question break at the end before our post-seminar discussion. So with that, Andrew, welcome. We're looking forward to your talk.
Well, thank you very much, John, for the extremely kind introduction. And thank you very much to the entire VAMOS committee, both for setting up this really great seminar series and keeping people connected through the very complicated last half year. And in particular, thank you very much for the invitation to give the seminar today. It's a real privilege. So as John said, I'd like to talk to you today about different ways that we think about or explore many-body dynamics that are dissipative, whether we want to or not, with cold atoms. Both looking at, characterizing things that we don't want to happen and understanding what that does to the dynamics of the system. And then also really looking at how you can engineer dissipative dynamics maybe that you're interested in or that you specifically would like to see with cold atoms. And, the picture that I have on my first slide here, I always like to have pictures of Scotland. This one is one of Loch Lomond, and Ben Lomond is the mountain you can see in the center of the picture. And of course, if you live in Glasgow, this isn't very far away. It's about an hour from here. So this is our environment. And so as a quantum optics theorist, I always like to say it's always very nice to explore your environment and all the great things that you can see and experience there. So dissipative dynamics are interesting. The environment is not just something that you don't want. So let me start by thanking the people in my group who have been involved in work, both that I'm going to specifically present in the seminar and many things related to it. This is one of our most recent group pictures taken during one of our typical weekly group meetings. And again, there are various aspects of things today that I'll touch on that are related to work by all the people in the group. But in particular, I'll be talking about things that have been done by Stuart Flanagan and by Francois Daminet. So over the course of the last few decades, we've had a lot of fun in the AMO community thinking about many-body dynamics in strongly interacting systems that we can engineer in a range of contexts with, for example, cold atoms and optical lattices, or various systems with long-range interactions such as trapped ions or arrays of Rydberg atoms or polar molecules in optical lattices. And all of these have a few sort of characteristics in common. Basically that, what makes these things special is the level of control and the level of microscopic understanding that we have over these systems, really starting from first principles. And this is something that sort of contrasts the wonderful and varied many-body dynamics that you also see, for example, in solid state systems. Because here we're normally dealing with, for example, atoms trapped in laser light in the middle of a vacuum chamber. And so you can start with sort of very well-known single particle physics and how the atoms or molecules are trapped with light. You can then characterize from first principles also collisional interactions between atoms or dipole-dipole interactions you have for polar molecules or for Rydberg atoms, or mediated interactions in ion chains. And you can go through and from first principles, derive the microscopic models and understand also the control knobs that you have in the experiment to change the different parameters of the models that come out. So for example, when you've got atoms and optical lattices, you have a Hubbard model, or if you have bosons, you have a Bose-Hubbard model, where atoms tunnel between neighboring lattice sites and they interact if two or more particles sit on the same site. And you can control this by changing the depth of the lattice or by using magnetic fields to control the scattering of two particles in the lattice, so through Feshbach resonances, for example. And what we get out is indeed the possibility to look at, over long timescales, coherent many-body dynamics associated with these models, or indeed to start looking at the thermodynamics or quantum phases associated with low temperature properties. And these are things that we've talked about a lot, and there are many exciting new directions in this. What we maybe don't talk about so much is that one of the really nice aspects is the level of microscopic understanding also from first principles that we have over the dissipative dynamics in these systems, and how important that is for characterizing to what extent we really can look at this sort of coherent dynamics in the experiments. So why am I interested in dissipative many-body systems? Why should we be interested? Is it not just the case that you'd like your nice Hamiltonian dynamics and that when we couple our system to some environment that we put it in, that the environment is in a sense just a nuisance? Well, you can answer sort of the question of why should we be interested in a couple of different ways. Fundamentally, of course, as much as we try to isolate a quantum system, all of them are open, at least at the point where you go to measure them. And so in a sense, it's something that we have to worry about, even if we might not like to. But in particular for atomic physics systems, actually, we find that the properties of coupling to the environment are often very nice and often surprisingly well controlled. So if you take, for example, the simple model of a two-level atom coupling to the external electromagnetic field, and you think about spontaneous emission from an excited state of the atom, then we know that there's a really nice separation of frequency scales where if you take, for example, rubidium in its excited state, you have an optical frequency of the order of 10 to the 14 hertz. You have a typical decay line width of the order of 10 megahertz or so. And so you have this sort of big frequency separation between the frequency of the photon that's being emitted and the 1 over the time scale on which that photon is being emitted. So you can have essentially a whole set of approximations as a result of that in quantum optics allow you to derive microscopic models, again, under very well-controlled approximations. And then having understood the dissipative dynamics, start to use it to create tools. And so if you think about it, everything that we do in cold atoms laboratories in order to get atoms cold and start manipulating them relies on our ability to cool the atoms using laser cooling techniques, to put them in the same internal state through optical pumping. These are all sort of processes that involve really careful control of the connection to the environment and engineering dissipative dynamics on a single particle level. And of course, this goes beyond atomic physics and quantum optics. This is also something well known, for example, in nuclear magnetic resonance, where people talk about things like algorithmic cooling, and where you have dissipative quantum control techniques across a range of different aspects of quantum chemistry. Again, by understanding the environment well, they can do things that they might not be able to otherwise. So this applies also to mini-body systems now that you make with cold atoms or with trapped ions. And there are many ways in which you see dissipative dynamics manifest itself in labs all around the world. The most obvious thing, a generalization of what I said on the previous slide, is of course light scattering, for example, from trapped atoms and optical lattices. But also there are now many setups around the world, including by three of the organizers who are on the Zoom call this evening. So Dan and Monica and John all have cavity setups with cold atoms. And here you have sort of natural dissipative dynamics in the way that we normally think about it in quantum optics, with light leaking out of a cavity. And of course, you also have, in both this scenario and this one, spontaneous emission from the atoms as well, that naturally gives rise to dissipation. And again, sometimes maybe you want the dissipation because you want to cool the atoms or to control their states. And sometimes you don't want it because it gives you decoherence when you're trying to look at Hamiltonian dynamics. You also have a variety of other processes that are often unwanted, but sometimes very interesting in their own rights. For example, there have been really nice experiments, again, in the last decade and a bit, looking at dynamics of collisions between either Feshbach molecules or polar molecules that are, polar ground state molecules that are reactive, where if you get two or more particles on the same site, it will lead to large loss. And you can have this in the case of two-body loss. It also works for three-body loss in more general cold atoms experiments. And if the loss is strong enough, actually it can suppress the tunneling that would populate a doubly occupied site. And you get things like the quantum Zeno effect that comes out of the dissipative dynamics, sort of suppressing double occupation. You can do the same thing indeed with three-body loss and triple occupation. And you have the same sort of thing. You can go and engineer dissipative dynamics also, for example, by taking atoms in an optical lattice or in a harmonic trap and immersing them, for example, in another species of very cold atoms, for example, a BEC of a different species. And in each of these cases, generally speaking, there is a large energy scale that allows you to make the same sorts of approximations that we do in single particle quantum optics, and allows us as theorists to write down microscopic models from first principles for dissipative dynamics in these systems. So again, with the light scattering or light leaking out of cavities, the timescale on which these processes occur, spontaneous emission or cavity decay, are normally much, much longer timescales than 1 over the optical frequency, which is 10 to the 14. So all of these megahertz, gigahertz processes are much, much slower. And so again, these same approximations can be used to derive models for the dissipative dynamics. In these examples here, very often the loss is much faster than the corresponding dynamics on the lattice, so you have the same thing. And here, your large energy scale is normally, for example, the separation between bands, in particular if you want to look at a lattice of particles immersed in a BEC. So these all give really interesting environments for studying dissipative dynamics in potentially strongly interacting many-body systems. So let me give an example of that, seeing as though I'm talking about many-body physics and light scattering. So when we start thinking about fundamental limitations for looking at cold atoms and optical lattices, one thing that we can never fully get rid of is the heating due to spontaneous emission, which after some time is always going to happen if you're trapping atoms, even with far-off resonant light. But if the light is far-off resonance, we can again go through and make all of the approximations that we normally would make in single particle quantum optics and derive, for example, many-body master equations that describe the process of decoherence due to spontaneous emission of photons from far-tuned laser light. So this sort of follows on again from sort of single particle dynamics that goes back to Gordon and Ashkin, for example, in the early 1980s. But here you can do this for many particles and then start to understand the physics of what you're seeing with heating in these experiments. And the key ingredient of the physics when you're looking at spontaneous emission with far-off resonant light is essentially this, that if you scatter a photon, if the atom scatters a photon and it goes out in a random direction into its environment, it gives the environment information about where the atom is. So what you see in the structure of this master equation, which is an integral over density operators in space, is that this tends to want to make the state of the atoms diagonal in space. If you start with a particle that is delocalized, for example, across your lattice, so this blue line is the wave function, then what's happening is you're scattering a photon, and that photon goes out, gives the environment information about where the atom is. And so it takes this superposition of the atom is here or here or here or here, and if you don't measure the photon, decoheres it into a probabilistic mixture of the atom is here or here or here or here, rather than a coherent superposition. What is the corresponding length scale? Well, it's the only length scale that's sort of left in the problem when you scatter a photon. It's essentially, it's the wavelength of the light that is scattered up to a factor of 2 pi. So typically in most optical lattice experiments, it tends to lead to localization of the particles on a scale of about a lattice site. It can also lead to heating of particles to higher bands in the lattice. Some people interpret that as if you like, finding out information about the location of the atom within a lattice site, which is also a very appropriate way to interpret that. And this tends to be suppressed by a Lamb-Dickey factor that, again, in typical optical lattice experiments means that if you're scattering, for example, red-detuned light, where the trap is bright where the atom sits, this process tends to be a bit less than, or a bit more than 1 in every 10 photons that you scatter spontaneously. So this is sort of how you can do that. And then, of course, you can take that and you can start saying, well, how does this affect the many-body dynamics? But in order to do that, you have to be able to properly solve the master equation and understand especially how the energy that you input into the system in this way thermalizes. The question is then, as theorists, how do we go about solving these sorts of problems, especially when you have many atoms in an optical lattice, so you have a very, very large Hilbert space. So what we normally do is we use these techniques that we refer to as matrix product state techniques, or as tensor network techniques, or time-dependent DMRG. These are all names for things that are algorithmically often a little bit different, but mathematically essentially the same basic concept. So we have essentially a set of coefficients that sort of specify the state of our system. And normally, if we grow the length of the system, the number of coefficients that we have to store in order to represent the Hilbert space grows exponentially with the size of the system. So what I've drawn here is essentially something that represents this tensor by saying that we have essentially these M indices that would describe, for example, the local states in individual parts of the system. So for atoms in an optical lattice, these could be the individual Hilbert spaces are individual sites. and the different states that you would have would be the different numbers of particles you could have on different sites. So normally this grows exponentially. What we do in a matrix product state is we decompose this large tensor into the contraction of a whole lot of matrices of some fixed maximum dimension. And so this dimension is given a number of different symbols, but here we'll call it capital D. The point with this is that provided that you have small amounts of entanglement across your system, which normally happens if you are at low energies in a 1D system, or if you have short time or near equilibrium dynamics, then what happens is your entanglement remains relatively small, and this turns out to be a very accurate representation of the states that you get. You can represent many-body ground states in 1D systems to machine precision this way with relatively moderately sized matrices, the order of a few hundred or a few thousand in dimension. So this is sort of how we often calculate dynamics. These are the state-of-the-art methods, if you like, for out of equilibrium dynamics in 1D many-body systems at least. And so how would we then go about calculating many-body dissipative dynamics this way? Well, one way is to build not a pure state, but a density operator. And this is one way that you can do it. And there are some technical overheads and complications, but for certain problems, this can be the best way, especially if you're looking to get very accurate average values for the master equation. The other way that we import from numerical techniques that were developed in the early 90s in quantum optics is to take pure states expressed as matrix product states and to calculate these master equation dynamics instead by stochastic propagation of pure states. So this is something that we refer to as quantum trajectory techniques. And the idea here is that we have a density operator that describes the state of our many-body system. And of course, it's a density operator because once your system starts coupling to its environment, there are many different ways that things can happen. And if you trace over all of those possibilities in the environment, then what you need to do is to express essentially the classical uncertainty we have as to what the quantum state of the system is. So you have, for example, a Lindblad form master equation like the one that we've got here. And then you can unravel that into stochastic trajectories of pure states in ways that in some senses are actually very physical. So imagine that you are trying to describe the dynamics of a driven or just an initially excited two-level atom. And imagine that you're going to do an experiment with photodetection, where you were going to look at the environment and put a photodetector there, and it would go click when a photon was emitted by the atom. So there, what you would see if the atom was initially excited and not driven is that at some point your photodetector would go click and you'd know that the atom had decayed and it was in its ground state. So this type of picture written properly in continuous measurement theory and quantum optics gives rise to this idea of quantum jumps, where you can stochastically propagate pure states to reconstruct on average the dynamics that come out of this master equation by thinking about propagation under some effective Hamiltonian, and then jumps that occur that here would correspond, for example, to an atom decaying. In our case of light scattering and optical lattices, this will normally correspond to an atom somewhere in the lattice spontaneously emitting a photon. You can also do this a different way, though. So also back in the early 90s, there was really nice work by Jazan and Percival, who developed ideas for quantum state diffusion as a way to unravel this master equation. And this is the same sort of idea, but if you were performing balanced heterodyne detection, mixing the light coming from the atom with a strong local oscillator, so a laser beam in a coherent state, and then subtracting the photo counts that you got here in order to give some continuous trace. So this gives essentially a stochastic differential equation that, again, if you average it over different samplings of the noise in the stochastic differential equation, reconstruct the behavior of the master equation. So what we've been doing is combining these sorts of techniques with matrix product states to allow us to propagate these sorts of master equations and study dissipative dynamics for, in particular, cold atoms and optical lattices. To give you an example of the sort of thing that comes out, you can take a model for which we can solve for a lot of parameters exactly. You take sort of hardcore bosons in a one-dimensional lattice. So these are strongly interacting. There's at most one particle per site. And if these start in the ground state and you look at the kinetic energy of the atoms in the lowest band of the optical lattice, they initially want to start where this red dot in the middle is. Okay, they want to start at close to zero momentum, zero quasi-momentum in this case, where the kinetic energy is lowest. What happens is if atoms then scatter light spontaneously, you'll end up increasing the energy as a result of that, because when the environment gets information about where the particle's position is, if something's very localized in position, becomes very delocalized in momentum. This spreads the particle over the lowest block band, heating it up and increasing its kinetic energy. And so these lines, the red line and the blue line, are sample quantum trajectories combining this sort of quantum jump type technique with matrix product states in order to propagate in time this sort of master equation. In this particular case, you wouldn't necessarily need matrix product states, but as soon as you add a finite interaction energy, you do. And what you see in the traces again is these jumps that lead to an increase in the kinetic energy. If you average over many of these trajectories, you get then a statistical sample, and you can calculate things like the average kinetic energy in the master equation with error bars, okay? And you can calculate for this very particular example, what you expect that kinetic energy to be exactly as a function of time. And you can see that with sampling a few hundred or 1,000 trajectories, you typically get a very good representation of what comes out of the master equation. And the statistical error, as with any independent samples, goes down as the square root of the number of samples. And we can then generalize that to a number of different systems. In the past years, we've been thinking, for example, about how the information that the environment gets about where the particles are tends to lead to heating and delocalization of atoms in a Minibody localized state. You have, for example, a disordered system where your particles are localized by the disorder. But if they're delocalized over several sites, what happens when you scatter photons, you get information about where the atom is, it's then localized somewhere else. It can then start to spread in the disorder potential, and actually this will always lead to diffusion of the particles over the whole lattice. What is interesting is to see the medium time dynamics and the competition between interactions and dissipation, which you can start to look at in these experiments. These experiments are sometimes complicated, they're sometimes complicated also by the fact that you can have atom loss. And this is a fascinating study where we collaborated with the experimental team of Uli Schneider and Emanuel Bloch in Munich, and also together with Ehud Altman and Mark Fisher, and with our other collaborators, looked at sort of theory and experiment comparison for these sorts of dynamics in experiments. And with Mark Fisher, Jorge Yago from our group, and with Evert van Nevenberg, we also went further and looked in more detail at how you could understand, using appropriate symmetries in your matrix product states, loss of fermions in these systems, and how you would get different dynamics actually if you had hardcore bosons versus fermions and started looking at loss in these systems. So there's a lot of fun things that you can do there. what I'd like to do in the second half is to pick out a couple of examples. One of them really benchmarking how the sort of dissipation that you get in these systems leads to errors and how it affects our abilities or doesn't, particularly depending on the numbers you have in the situation you look at, to extract reliable correlation functions out of dynamics in these systems. And then I also would like to talk about how we can start using some of these techniques to start thinking about transport systems with cold atoms and study those theoretically, or think about engineering transport dynamics with cold atoms experiments. But I'd like to pause there and offer the opportunity for people to ask questions.
Fantastic, perfect timing. Okay, so we do have a number of questions. The first is, as is traditional, from Bill Phillips. He says, with regards to localizing atoms by light emission or detection, what if you insist on detecting the direction of the emitted photon, giving you momentum information, rather than the position of the emitted photon, giving you position information?
So this is an excellent and very good question, Bill. So what we are thinking about here is a situation where the photon is scattered in a random direction, and from that, what comes out directly is essentially information more or less about where the photon comes from, and it allows for this type of decoherence. What we're talking about also here is thinking about these dynamics in the case that we don't know what the measurement result was, if you like, in the environment. If we instead put detectors sort of that were able to take the momentum information specifically of the photon and tell us this photon was scattered in this particular direction, then of course we can infer more information about the state that we have after that photon is scattered. That's sort of a different discussion. But it doesn't matter what you detect if you don't look at the result of the measurement and you average over all of the possible measurements that could have occurred. Then here, because you have this Markovian coupling between the atoms in the lattice and the environment, the average result is still going to stay the same. You've traced out the environment, so the average description is this one of the particle being localized.
So that is to say, maybe whether you localize the recoil and momentum space or the position, when you average over it, you get the same answer.
When you average over the same thing, the average over it, you get the same thing.
That's very interesting. Okay, so this is a question from Dan Stamper-Kern. So we recently heard a talk from Ana Asenio Garcia about collective scattering effects and how that can qualitatively change the physics. So the question is, under what conditions does one need to modify the light scattering master equation treatment to account for collective scattering effects, e.g. superradiant emission?
Okay, so that's a great question. So there are essentially a couple of different things in that. So what we have assumed here in deriving the master equation, so I'm on the right slide, is that we are dealing with very far tuned laser light. And so in this case, what's happening is that you're always getting the same types of processes in terms of sort of local collective excitation and spontaneous emission of the photon. This master equation properly accounts for collective effects, and you'll see that because the things are always symmetrically excited, because we're far tuned here, you'll always get essentially a superradiant mode produced. So you will get more light scattering if you've got two particles. So if you've got two particles on a site, then the scattering rate goes up essentially by a factor of 4 in this particular case. If you're in sort of if you're in red detuned traps where the atoms sit in the light, for example. I'm trying to think of other specific examples, but so long as you have two identical atoms scattering into the same mode, you get superradiance directly out of this master equation. Now, if you include the excited states, of course, you can come up with a much richer problem where you can actually see and populate by driving the system in different ways, sort of closer to resonance, different types of superradiant and subradiant modes as well, and you know, all sorts of collective modes in between. And it's a great problem. Here, things are simplified to the superradiant effects by having very far-to-tune driving light.
Cool. Thank you. Okay, so this is actually a pair of questions that go together. Ivan Deutsch asks, what do you see as the pluses and minuses for the quantum trajectory approach versus matrix products operators? How do you deal with the positivity of the density matrix? And then Sunwon Choi asks, what are the advantages of using stochastic evolutions of matrix product states rather than direct matrix product operator simulations?
Okay, so those are fantastic questions. So so thank you very much. So essentially, there are two things that one has to consider when you're propagating these tensor networks in general. One is what is the local bond dimension? Because the bigger that is, the more expensive the simulations are going to be. And what is the matrix dimension that you need to describe entanglement and correlations within the system? Because when we're contracting these matrices in order to express our state, it's the size of the matrix and therefore the amount of information in this contraction when we multiply out the matrices that gives us the correlations in the system. So the complication of the density operator approach is that it requires the square of the local Hilbert space dimension. And then also it requires that the matrices are large enough to express classical correlations in the system as well as entanglement. And so the downside of this is that the matrices have to grow larger in order to express classical correlations in the system. The stochastic approach is nice because it removes the requirement to square the local Hilbert space dimension, so you win to begin with, and also the states don't have to express the classical correlations in the system because you get that out of stochastic averaging. It's the classical correlations come from correlations within one trajectory versus correlations in another trajectory. The downside is that depending on the type of dissipation that you have, the jumps that you would get here, for example, can take you far from equilibrium. And because of that, you may find that the entanglement that you have in your pure states grows much more rapidly than the entanglement that you get in a density operator like this. So the short version is that unfortunately it depends on the problem, and you have to try different things for different problems. We've often found for short-time dynamics, it's much easier and much more straightforward and normally very accurate to do things with the stochastic methods. But especially if you want very long-time evolutions, you can sometimes win if you've got dephasing that keeps your entanglement and correlation small. Sometimes you can win by going to long time scales with this density operator approach. And that was what we found, especially in this type of work when we had systems that we wanted to propagate for long times because we were looking at many-body localization combined with exactly this type of dephasing that tended to reduce the correlations.
Thank you. Perfect. So we actually have a countably infinite number of questions, so we could enumerate them, but I think we should stop for now and let you move forward with the second half of your talk.
Okay, perfect. Thanks, John. Okay, so I have to be a little bit careful of time, which is always a little bit interesting on Zoom. But I'm going to highlight some sort of key points then of two examples of things that we've been working on recently using these computation techniques for dissipative systems and thinking about how to characterize dissipation with cold atom systems, and in one case, how to engineer things that we'd like to see happen in dissipative dynamics with cold atoms. So the first of these questions is really, from a theorist perspective, trying to get at the answer to the question, under what conditions can we reliably think of cold atoms as a calculator? Essentially, when can you do analog simulation in a way where you're trying to extract, for example, some correlation function out of the dynamics, and you'd like to show that you have a practical quantum advantage in the sense that you can reliably calculate something that you can't calculate on a classical computer. And of course, we're very inspired by the wonderful advances in the last years with looking at, for example, fermions and quantum gas microscopes and these wonderful experiments at Harvard and at MIT and in Munich and at Princeton, various different places, and in Toronto. And also colleagues of ours at Strathclyde. There are many people doing really interesting things with fermions and quantum gas microscopes, looking at dynamics and static properties of the Hubbard model. Of course, one of the long-term goals is to understand the low temperature behavior of this type of model. But if we want to make a comparison with something where it's straightforward to characterize what a classical calculation can and can't do, as a theorist, it's much nicer to appeal to the dynamics because it's much harder to have a discussion about what our existing theoretical methods can and can't do and what their limitations are at calculating thermodynamics in these systems. On the other hand, if we do quench dynamics, where you start in a state that's not an eigenstate of the Hamiltonian and you propagate in time, generically, we expect entanglement expressed in terms of an entanglement entropy when we split the system into two pieces. We have a pure state. We ask, if we trace out one side, what is the entropy of the other side? This characterizes the entanglement. And we expect this to grow linearly as a function of time based on results of Calabrese and Cardi a number of years ago and various other authors. And in these papers, Norbert Schuh and Ignatius Sirac and the collaborators looked at how this relates to our ability to look at time-dependent dynamics in matrix product states. And the point here is that if you've got a matrix product state and you want to represent linearly increasing entanglement, then you need to have an exponential increase in the dimension of the matrix product state. What that means for us practically is that we can evolve to a particular time, and then to go linearly further in time is an exponentially larger cost classically. So here, in order to get up to TJ is just over 2 reliably, we are already sort of doing calculations that on a small cluster will take a few hours or a day. And if we want to go to here, then we're talking about weeks, and here to months, and here to years. And so it grows very, very quickly. And not only are we not able to represent the actual entanglement, but if you start looking at correlation functions, two-body correlation functions, single particle correlation functions, the errors grow rapidly, essentially to errors of the order of the actual values of the correlation functions that you're trying to extract. So these become errors of the order of 1, growing rapidly, and trying to reliably extract something like this at long times beyond sort of actually even just a few tunneling times in the experiment becomes very difficult. So the question is, could you instead go and reliably extract these dynamics from a cold gas experiment where you implement this in an analog quantum simulator? And again, what I want to emphasize here is that the microscopic models are well known from first principles, including the dissipation. So we can go through and we can try to write down a model that includes all of the key errors. And so one thing that we've been doing in our group, particular calculations by a former postdoc, Anton Boyeskich, that were then taken over by Stuart Flanagan, a current PhD student in the group, we're basically looking at quench dynamics here, but accounting for all of the errors that we can think of as theorists and that we know from first principles can occur in these experiments. starting from calibration errors, unwanted Hamiltonian terms, because we've made approximations in producing the Hubbard model for a particular set of parameters, errors in initial state preparation, and then heating due to noise or decoherence from spontaneous emission. And what we find is that if we put in values typical of current experiments, that the dominant error in short time dynamics comes from uncertainties in the calibration of the lattice parameters from shot to shot, and specific calibration of tunneling and interactions. And that in typical experiments, they seem to lie at the moment somewhere just a little bit below the 1% level. But the nice thing is that these errors, when you look at single body, two body correlation functions or string correlation functions of the sort that have been extracted recently in quantum gas microscopes, what we typically see here is that the errors tend to propagate relatively slowly through the system. Partly this is because the Hamiltonian is local, the errors are local, and there is essentially a Lieb-Robertson bound for propagation of errors here. And what we see is that the actual effects on the correlation functions tend to remain well below the sort of 1% level, even at a 1% calibration error. And if you can get that down to 0.1%, then these are even smaller still. The ultimate limit of how far you can go in time is really a question of the decoherence time of these experiments. And you do see the effects of spontaneous emission if you were to scatter light relatively quickly. Again, using this master equation from before, we can model that directly. And we can see how the errors in these correlation functions increase over time and do indeed get up to the few percent level and start to get up to values where this might not be reliable. But what I want to emphasize here is that for far tuned optical lattices of the type that people are dealing with, the current values are really of this order. We've cranked up the values in order to see the effects before we can't calculate anymore in our classical calculations. And what you see is that over short times, these things remain very, very small. So we went through an analysis of a number of other elements of this, but the bottom line is that we would expect with current errors in optical lattice experiments that you can build a 2D system of 10 or 20 by 10 or 20 lattice sites and atoms, and that you should be able to reliably extract these sorts of correlation functions, at least in terms of the calibration here, if you make enough measurements, to within the percent level in a way that you couldn't from the equivalent classical calculations. So in that sense, choosing the rules of the game the way that we have in this analysis, I think it's strongly justified to say that we really do have, in that sense, a practical quantum advantage already in quantum simulators that we can, in principle, test by going and looking at all of the effects that we expect to see from first principles appearing in the experiments. Of course, we can make similar comparisons, and in collaboration with Matthias and his team and with Peter and Emmanuel, we've been thinking about comparisons between analog and also digital quantum simulators. Digital simulators have a downside that you need to go and basically, and for example, express the time evolution using trotterization of the time evolution operator. You don't have a native implementation of the Hamiltonian, so for our comparison, this has sort of home ground advantage. And they have the upside that if you really build a digital quantum simulator, that you can then go and look at the dynamics of any model with that digital quantum simulator. But a fault-tolerant digital quantum simulator would require more than 1 million gate operations to do a trotterization of the time evolution that was as accurate as current analog experiments are able to get to with the typical current calibration errors. So long as you have a native implementation, then in the foreseeable future, that will win for looking at these sorts of quantum dynamics. That's even if we have fault-tolerant gate operations. NISC is another story there. So in the last little part, what I want to talk about is I've been emphasizing what we can do on a microscopic level if we can make the Born approximation that we're weakly coupled to the environment, make a Markov approximation that, say, if we emit a photon, that it runs away very quickly, and make a corresponding rotating wave approximation, we have this large optical frequency, so we're only going to have energy conserving terms in the interaction Hamiltonian. And I'm going to ask what happens if we want to go beyond these sorts of approximations for looking at dissipative dynamics, especially with cold atoms. What I should say from the outset is that, of course, this is an enormous field looking at non-Markovian dissipative dynamics on its own. There are many people who have made major contributions over a number of decades. There's a beautiful review by Ernest Vega and Alonso just a couple of years ago in Rev Mod Phys. What I'd like to focus on is sort of specifically the sort of AMO question and how we can take these mini-body systems and look sort of beyond the Born-Markov approximation with the type of calculation techniques that I was mentioning, and then think about interesting physics associated with that. So one question you might ask is, why actually is it necessary to think about non-Markovian dynamics? These AMO systems are so often very nicely sort of separated in their frequency scales for coupling to the environment. You have at some point sort of Markovian dynamics. You know, if you have atoms in a cavity, you've got Markovian dynamics once the light leaks out of the cavity. So why is it really necessary? And I'd give two answers to that. The first is, sometimes you have a physical system where you are interested in seeing genuinely what happens when you go sort of beyond just weak coupling. For example, you might have transport systems where you'd like to go beyond sort of, you know, a perturbation theory approach in understanding how, you know, some sort of channel couples to leads. Maybe you're trying to represent some sort of systems in the solid state, for example. Or maybe you're trying to do a calculation where, for example, you've got atoms in a cavity. You would like to write down an effective model for the spin system for the atoms in the cavity because you'd like to solve it with time-dependent DMRG. If you have a multi-mode cavity, your Hilbert space might be too large. And so maybe rather than making the cut between system and environment at the edge of the cavity, where this would be nicely Markovian, maybe you would really like to eliminate the cavity modes as well. Especially, again, in a multi-mode cavity, this can be huge in terms of the Hilbert space that you're describing. So maybe you want just an atom-only version of this. And at that point, of course, you've got often difficulties in eliminating those modes because you're often going to be coupling at different frequency scales. This is especially true if we try to, for example, implement a Dickey model in the cavity. So it turns out that there are really nice techniques, again, that we can take over from few particle physics into the mini-body context. What we've been doing is going back beyond where we made the rotating wave approximation, going to Redfield master equations, which we find work very, very well for a number of these systems in expressing dynamics that go beyond particularly a rotating wave approximation. And in particular, that we can go to even sort of cases that have that go beyond the sort of the Born approximation and properly weak coupling by using a method that was developed in the group of Walter Strunz in Dresden, which they refer to as the hierarchy of pure states method for expressing a quantum state diffusion equation. So the key for us in terms of doing the calculation is to use the second type of method that I had under quantum trajectories, to use quantum state diffusion and to use these so-called hierarchy of pure states techniques to go and calculate with atom practice. So this allows us to derive and calculate atom-only versions of the dynamics of spin systems and cavities that are coupled to the environment. And it also allows us to start thinking in a different form about these transport systems. And we've been motivated to think about transport by a number of recent experiments, both developments in looking at new transport geometries that can be engineered in solid state physics, but especially by the cold atoms experiments in Zurich and now Lausanne by Tilman Esslinger and Jean-Philippe Brantou, and also indeed by our chairs experiments, looking at, again, sort of transport in the sense of energy or photons sort of moving in a lattice, coming from some drive and dissipation in some part of the system. So what we've been trying to do is to apply the techniques that we use to look at many-body dissipative dynamics in cold atoms, really to calculate non-equilibrium dynamics in these systems, to try to understand how dissipation in the channel, if you have dephasing or atom loss, affects things like this sort of transport dynamics, and maybe asking sort of how we can use that to engineer interesting phenomena in those systems. So what we started off with is thinking about this sort of transport problem of leads coupled to some channel, which might be, for example, just a single trap, a little bit like a single trap version of this, this cold atom experiment of Tilman and Jean-Philippe. And what we've done is we've written down, again, the corresponding master equations. We need to write down a Redfield master equation because you end up with a multi-frequency drive, especially if you have Cooper-Peer tunneling here. And so on a technical level, what we've done is we've written a Redfield master equation or a corresponding stochastic differential equation through essentially a quantum state diffusion equation in order to model this. The thing that we focused on in terms of one phenomenon that you'd like to be able to see here is something where there were the signatures seen already by Tilman and Jean-Philippe and their co-workers. This is an idea that in solid state physics was referred to as multiple Andreev reflections. It's the idea in superconducting leads that if you have a gap that prevents an electron from tunneling over to the other side of a junction, because you don't have a strong enough bias, that in fact you can get what we call subgap transport before the bias is large enough for the electron simply to go from here into the empty states over here, by having co-tunneling of Cooper pairs that decrease their energy. This increases its energy, and in a process in perturbation theory, you can have co-tunneling of single particles in Cooper pairs that give rise to subgap transport. It's normally difficult to write down a model that captures this in weak coupling, and it's also difficult to have weak coupling and to directly see sharp features are sort of associated with this, because if the coupling is too weak, normally the higher order perturbation theory processes are suppressed. So what we have been thinking about is a version of this where you might not just have particles flowing from the left reservoir to the right reservoir, but you might engineer something that looks like Cooper-Peer tunneling, for example, by coupling atoms out of a separate molecular BEC that could be connected into the junction in order to derive this Cooper-Peer tunneling. And what we find is when we look at that for typical parameters, that we see sort of strong subgap transport that can be controlled by the sort of by the coupling of Cooper pairs into the junction. And we can look at that not just at zero temperature, but also in different temperature scales to understand the effects that we might see if you went to engineer something like this, for example, in these experiments of Tilman and Jean-Philippe. I'm running a little bit out of time, but I just want to add to that we've also looked at what happens when you have, for example, particle loss or dephasing in the junction, how that separately affects the subgap transport phenomena that involve the Cooper pairs, for which the dephasing can be quite important, and what happens if you extract particles out of here that draws current actually in the end from both leads. This for us is sort of a starting point to think more closely about the things we might be able to calculate and explore in terms of these driven dissipative systems, either with atoms in cavities, with more general tunneling systems, to think about really time-dependent dynamics and maybe continuous measurement of these, and then maybe even to think about similar sorts of things in these driven dissipative Bose-Hubbard models that John and Dave Schuster have in their labs. So we'd be very curious to think more about those sorts of things as well. Just one more comment on the techniques. We have now combined this hierarchy of pure states with matrix product states, so should be able to do this sort of also again for certain classes of many particle systems. This works better if we have Barth correlation functions that we can express as sums of decaying exponentials. This is the main sort of constraint on this. And the matrix product state constraints are again that we don't have enormous amounts of entanglement building up in the system. With that, I just wanted to briefly say this is one part, obviously, of a lot of interesting things that are happening at the moment that we're very curious to couple in these dissipative ideas to. And we think also a lot about controlling dissipation and trying to move entropy to different places in a system, or to try to do cooling of systems and optical lattices or adiabatic stack preparation in order to try maybe in some of these experiments to get to lower temperatures. And we're also very interested in both combining these things with, for example, long-range interactions as you have for ions or Rydberg atoms or polar molecules, and thinking about applications maybe that go also beyond physics, or at least as far as building states for metrology and sensing, or maybe into things like quantum annealing. With that, let me summarize by saying that as a theorist, this is a wonderful playground. As always, we love thinking about these great experiments. That what's wonderful about the dissipation of these systems is that you so often can derive and express what's going on microscopically from first principles and start thinking about benchmarking things like when we're going to get a practical quantum advantage from dynamics of cold atoms, and how to understand things like quantum transport or dynamics in optical cavities. Thank you.
Okay. Thank you, Andrew, for a wonderful talk. Let's grab just a few questions before we break for the after session. So Timur asks, why would it be necessary to use a non-Markovian master equation in the regime where secular approximation breaks down? The Born-Markov approximation is different from the secular approximation, yes?
So the simple explanation is there are in a sense there are different levels of this. So the Redfield master equation, in a sense, is time local, but still has some time integral essentially over a Barth function in it. That essentially that goes beyond, if you like, what we have in a normal Lindblad form master equation. The issue that we normally get to, for example, with a Dickey model in an optical cavity is, if you like, we have two different frequency scales. If you don't make the secular approximation, you have this combination that you excite an atom and you create a photon, as well as that you excite an atom and absorb a photon from the field. So what this normally corresponds to is having, if you like, sort of multi-frequency drives. You will often still have a Born approximation and a short time correlation function in the reservoir. So in that sense, a Born approximation at least. But if you end up with these counter-rotating terms, you can't derive a normal Lindblad form master equation. And if you try to make those approximations in certain models, you will explicitly get the wrong answer. And we can see that in this example here, actually, when we have atoms in an optical cavity, we know what the answer is if we make the cut where this is clearly, Markovian, and we can make a rotating wave particular approximation sort of out here, and we can tell whether or not we get the right answer then when we try to write an atom-only model for the single mode cavity.
Excellent, thank you. Okay, Anupam Mitra asks, how does the number of trajectories needed for convergence scale with the system size, and how is this affected by gamma?
Okay, so that's a very good question. So the number of trajectories that you need depends not just on the system size, but also on the quantity that you're trying to extract. So generally, if you're trying to extract a global quantity and you have local jumps in the system, so for example, in this type of case where you might get some local spontaneous emission of a photon, you have a local jump occurring, and in a given trajectory, you're going to have jumps in a few places, but not everywhere in the system. So if you're trying to then work out what some correlation function is locally on one site, then I would expect roughly that the number of trajectories that you need to do that grows in some form, perhaps even linearly with this, probably linearly with the size of the system, because you want to sample the dynamics properly on that single site. Whereas if you instead are interested in that correlation function averaged over the whole system, then you may find, very often you do, that actually the number of trajectories you need is independent of the size of the system.
Cool. Okay, so I think our Q&A is going to be a Bill Phillips sandwich. So the last question of the day is from Bill. He says, why does atom only for a cavity problem make it non-Markovian? Okay,
so the answer is essentially, the answer is essentially this, that in this case, what you are doing is your atoms essentially can decay into the cavity and then reabsorb the photon afterwards. So of course, if you make the cut at the edge of the cavity, it's perfectly Markovian, because once this photon has left into the vacuum modes of the radiation field outside, you've lost it, and on all the relevant timescales, it's gone. Whereas here, if you try to eliminate the photon modes inside the cavity, then you can be in a position where essentially the atoms modify the light in the cavity, and then that light in the cavity modifies the atoms again. To make the model make sense at all, you have to be relatively far tuned, but even more so when you get into a multi-mode cavity, you have one atom able to modify a cavity mode and then essentially feed back into the atom. And again, you get, in principle, many different frequency scales for that, which is why the normal sort of rotating wave approximations that we make start breaking down. Especially, I should say, when we engineer Dickey mode type coupling, you can do this if you just have a Jaynes-Cummings model. Then if you are in a far tuned regime for a Jaynes-Cummings model, it does work if you just use a Lindblad master equation. But as soon as you've got the Dickey terms and the counter-rotating, it's problematic.
Wonderful. So again, I apologize that we didn't get to all of the questions. If you have an additional question, let me mention that in a moment would be the perfect time to hop over to the post-seminar discussion posted in the chat and on YouTube. But before we get to that, I'd like to announce the upcoming talks. So Andrew, if you could unshare your screen for a moment, I would be in your debt. Okay. So the upcoming talks, next week, the Quantum Science Seminar is on a break, but the following week on Thursday, October 8th, Peter Zoller will give the Quantum Science Seminar talk. As Andrew, of course, knows, because he's a host of the Quantum Science Seminar, but you know. Next week, the VAMO speaker, same day, same time, Friday at 12 noon Pacific, will be Wes Campbell, talking about stability means never being excited, and that's no fun. So with that, let's thank Andrew again, and hopefully we'll see all of you over in the post-seminar discussion.